Hi all, let's do an application of the chain rule. So in some sense, we'll see tons of problems that are applications involving the chain rule. Anything you make up where the function is a composite function and it's part of a word problem, you'll have to use the chain rule for. But this is a specific type that I want to tackle. What's really going on here is that we don't have the functions already composed, and it will save us some really messy derivative taking if we use the chain rule to not have to build that composite function and then take the derivative. So let's just pick apart what we really have here. We have a P of t function that gives us the population of a city in thousands as a function of the number of years since 1995. And then we have a g of p function that tells us the number of garbage trucks needed when P is the population in thousands. So inputs population in thousands, outputs garbage trucks. So I can already see here that if I could make a G of P of T function, that would be a useful function. It would input years and it would output number of garbage trucks needed. Okay, so we want to find the value of each of the following in 2010. So I can already see that I need to be a little bit careful because my time variable is defined as number of years since 1995. So 2010 is 15 years after 1995. So I'm really looking for P of 15. And P of 15, I just need to plug that 15 into this messy function, e to the negative 0.02 times 15. And that's just calculator work. And if I plug that in correctly, I get about 13.145, meaning that in 2010, the population is about 13,145 people. Next on our list is to find G of P for the year 2010. And this is where we want to start to be careful, and I want to really make the point of the one kind of tricky detail in all of this. I do not plug 15 in for P. 15 is a T value. So what I need to know is what is the population in year 15. And then if I plug that into my G function, it will tell me the associated number of garbage trucks. Lucky for me, I just did that. So I am really plugging 13.145 into G. For this one, I got about 26.12. This is number of garbage trucks, so I don't even know that I need the 12. If I was going to interpret this, I would just say I need about 26 garbage trucks. All right, next on my list, I want to figure out the value of dp dt when t equals 15. So to find the derivative of p, let's see, I'm going to use a chain rule. So we could do this with quotient rule, but I actually think it's a little easier with chain rule, and this is a great time to show you that. I could rewrite this as 130 times 1 plus 12e to the negative 0.02t, all raised to the negative 1. It is really tempting to say I brought that 12e to the negative 0.02t up, so it should become positive. But you're not bringing it up as its own piece. It's attached to that 1. So it really needs to be the whole thing to the negative 1. If I am now going to apply derivative shortcuts, the outer function is, well, let's start with this. The 130 is a constant multiple. It just sticks around. The outer function is that negative first power. So if we think x to the negative 1, the derivative would be negative 1, which would drop down and multiply by that 130. And then the new power would be negative 2. And in this step, I would not change anything about that inner function. Negative. Okay, this is also a really good example just for a messier chain rule. So I'm going to go back up above and I'm going to keep track of what I've done. I've dealt with the 130 and I've dealt with the negative first power. I have not touched 1 plus 12e to the negative 0.2t in terms of taking derivatives. So now I need to chain out the derivative of that function. And interestingly, that function also needs a chain rule. So you will, not that uncommonly, get nested chain rules. You can keep applying the chain rule as many times as is needed to get rid of composition. So here I take the derivative of 1 and get 0. I carry the 12 down. The derivative of e to a power is e to that same power multiplied by the derivative of the power. So this is an additional chain rule happening. The derivative of negative 0.02t is just negative 0.02. So that ends up being the derivative. And it's fairly messy, but I just need to plug in 15. So I can just run through each of these and plug in a 15, and then it just becomes calculator mess for me again, which hopefully I can do right. I got about 0.43. And that would be 1,000 people per year. So the population was increasing by 430 people per year is what that translates to. And this was fairly straightforward. I mean, messy derivative, but nothing too new or weird going on, because this was the derivative of p with respect to t, and p is given as a function of t. What gets interesting as we move on is that we'll see things that bridge between function p and function g. So we want to watch carefully for that. But this next one is still pretty good. dg dp makes perfect sense because g is a function of p. So we can go straight for the derivative, 2p minus 0.001p squared. The derivative is going to be 2 minus 0.002. That power rule drops the 2 down. And then it will be p to the 1. And now we're supposed to evaluate, figure out what the value is in 2010. We know that in 2010, P was 13.145. So that's what we'll plug in. And again, keep being very thoughtful about this. Deciding that t equals 15 doesn't necessarily say what p is. We had to do some work to figure that out. For this one, I get about 1.97. So this tells me that the number of garbage trucks is increasing by about 2 trucks per 1,000 people. So this one, yes, I think that does say people, looks funny, is not g as a function of t. It's not per year, it's per 1,000 people. Okay, so now kind of the culmination. This has been building up to it. We are asked to find the derivative of g with respect to t. And this is a little bit tricky because g is not a function of t. G is a function of p, and p is a function of t. So we are really being asked to take the derivative of g of p of t, which will become g prime of p of t times p prime of t. So again, we have to be really careful. We will use g prime, but we won't be plugging in 15. 15 is a t value. We'll be plugging in p of 15, which is our 13.145. So if we want all of this when t equals 15, we can just fill that in over here. So you just have to recognize when you get to the composite one where you have to plug one function into the other. And in that situation, we need to apply the chain rule. So we already have some of this built out for us. You won't always, but we know that p of 15 is our 13.145. So we will need g prime of 13.145 times p prime of 15, which we actually also already figured out. I kind of did the pieces for you. And then g prime of 13.145 is actually what we just did. We got 1.97, and the units can even be interesting here. This is trucks per 1,000 people. And then we're multiplying it by 0.43, and that was 1,000 people per year. So notice that our units, the people part crosses out, and we're getting trucks per year, which is exactly what we would want to get. So basically, it turns out that if you want to know how fast g is changing with respect to time, you multiply how fast g is changing with respect to p by how fast p is changing with respect to t. And when I go back and plug all of this in, I get about 0.847, so I'm going to go to 0.85 trucks per year. So in the year 2010, we're expecting the need for trucks to increase by about 0.85. So we probably want to buy one additional truck in the year 2010. All right. Hopefully that helps and didn't just make chaos. Thanks for watching.